Chapter 5, the time value of money. This is part 1 of Chapter 5. Following are the learning outcomes expected from students in Chapter 5. We will see and understand the meaning of interest rates. We will see the meaning of present values. In this chapter, we will talk about annuities and perpetuities and how we use them in corporate finance. We will see the meaning of effective annual rates and annual interest rates. We will see the correlation of inflation with time value of money. So, let's start with the definition of what the meaning of word future value is. It is the amount to which an investment will grow after earning an interest. The investment that we have today is called the present value. The value that this present value will attain after a particular time is called the future value. During this time, it earns an interest on itself at a specific rate given as rate of interest. Let's study this in more details. So let R be an annual rate of interest and T be the number of years. So in T years, a principal P will reach different values depending on how the interest is calculated. If the interest is simple, then the future value through simple interest is present value times 1 plus rate times time. Every year, we earn rate times initial investment. For example, if the simple interest rate was 5% and the initial amount was $100, then we'll keep earning $5 every year without reinvestment of the $5 that we earned from the first year. So every year that we earn $5, we get $5. So if we invested in 5 years, then we'd get 5 times 5, $25. Oh, bad example. We should have invested for 7 years. So 7 years times $5 per year gives us $35. We would end up with $135. That's the future value at the end of the 7 years. On the other hand, if we did compound interest, then every year that we end up with, that amount starts out as a new principal for the next year or the new initial investment for the next year. So every time we do that, we have to take the initial investment times 1 plus R. That is a new future value at the end of the year. So if T is the number of time periods, then initial investment times 1 plus R to the power T gives us the future value. Now, let's take a look at this in greater detail. For example, simple interest is principal or present value times rate times time by 100. We could just say present simple times rate times time. Now, amount or future value is principal plus interest. Now, we have interest equals principal times rate times time by 100. So, principal plus interest replaced by this, principal times rate times time by 100. I take out principal common. I'm left with 1 and rate times time by 100. So, 1 rate times time by 100. So, principal times 1 plus rate by 100 if time is 1 year. Now, this time becomes 1 year. Now, with reinvestment for more than 1 year, this is the amount with 1 year, right? So if I take that amount and I reinvest it, it becomes a new principal. So principal times 1 plus rate by 100 is the new principal times 1 plus rate by 100 is the amount after 2 years at the rate. So it becomes principal times 1 plus rate by 100 to the power 2. Now if we keep on doing this for n years, the amount will be principal times 1 plus rate by 100 to the power n. If we just redefine principal as a present value and amount as the future value, then we have present value equals future value divided by 1 plus rate to the power n. Notice we are using the word rate and rate by 100 interchangeably. If we just say the word rate, then it's a decimal number. If we say rate by 100, then the rate is an actual number. For example, if I say rate is 5, then it means it's 5% or 0.05. These three are used interchangeably. If I say rate is 5, then I have to divide it by 100 to convert it to a decimal. So I can add that 1.05 to the power n. So please remember this when we talk about rate of interest. So present value is future value divided by 1 plus rate to the power n. Or future value is present value times 1 plus rate to the power n. That's what we saw here. Future value is present value times 1 plus rate to the power n. Alright, now for n years, if we received n different cash flows, the first cash flow that we receive after 1 year is CF1 divided by 1 plus rate. Now that's the present value of the first cash flow. So these are n present values. We could say there are potentially n present value of each cash flow. When we add up these n present values, we get a single number, and that's the present value of all of these n cash flows. So the present value is defined as the present value of the first cash flow plus the present value of the second cash flow plus the present value of the nth cash flows. So I can simplify this as I can remove this plus sign and represent a typical cash flow as CFI divided by 1 plus rate to the power I. So 1 plus rate by 100 to the power I. And that's the term that I have here. Now I can put this in parentheses and say this is summed when I goes from 1 all the way through n. So I goes from 1 through n, sum of this parenthesis for all of these periods. So CFI divided by 1 plus rate to the power I. And that is called the present value of these n cash flows. And notice they are n present values, but when we add them up, it just becomes a single number or a present value of n cash flows. Now, let's just do an example of simple interest. If the rate is 7%, we invest it for 5 years and the principal is 100. With simple interest, the 100 will become 107 after first year, 114 after the second year. So we keep adding the $7. Now what's happening is we are pocketing these $7. So the $100 keeps working at 7% every year. 121, 128, and 135. That's simple interest. However, with compounding, what happens is after first year, instead of the $7 going into my pocket, the $107 start earning the 7% interest. So the new interest that we earn is not just 7, it will be 7.49. So $7.49. The second term will become 114.49. And the 7% will now, for the third year, will be 7% of 114.49, which is 7.85 almost. And that will be added to 114.49 to make it 122.2 something, 50. So the next 7% will be on 122.50, and that will make it 8.53 approximately, 8.58. And when we add 8.58 to the original value, 122.50, we get 131.08. And then the 7% for the fifth year will be on 131.08. Notice that the 7% for $100 is just for the first year. The principal for every year keeps on changing. That's the difference between the compound interest and the simple interest. In this case, I'm not taking away the interest amount with myself. I'm instead leaving it with the principal and letting that interest accumulate with the principal and earn a greater interest on itself. So that's the last interest I earn. So with simple interest, all these numbers of interest earned per year are $7, whereas with compound interest, they grow because the interest earns interest on itself. So value is greater for compound interest at the end of year 5 at 140.26 as compared to 135 with simple interest. So the power of compounding is that with 7% interest, now we could see this in Excel, for example, interest earned at the rate of 7% for the first 40 years on $100 invested using simple and compound interest. And let's see that in Excel. Launching Excel here. So here we go. So the problem said 7% for first 40 years. So with simple interest equals 100 times parenthesis 1 plus 0.07 times 40. That's the amount we'll end up with at the end of the 40 years. Or we could actually make a chart out of this. So if we want to make a chart, we can go to 40 years. 40 years. So this is year 1 through 40. And every year we have the original amount $100 equals 7% times that $100. well, we say dollar each, dollar two, and that is my new interest earned. So I add that to that plus $100. My starting amount principal is $100. Just copy and paste that formula and see the 380 at the end of the 40 years. So this is a simple interest earned. Now let's make the same thing with compound interest. Compound interest earned. Same, years 1 through 40. And the starting amount is $100 or $100. Now the principal, well, yes, equals 7% times the previous principal is $7, and the new amount is interest plus the principal. So when I copy that, this is going to increase to 7.49, as we saw on the slide, 8.01, 122. At the end of 40 years, this is going to be way more than $380. It's 1,497.45. So that's the to see it in a graph. Well, let's graph it. Line is fine. Okay, that's my simple interest. Now if I add compound interest, select data, series name, let's call it compound interest. Series X values are the same, and series Y values are right there. Okay, let's see how the red line compound interest, oh wow, look at the red line compound interest grow. As it accumulates more and more interest, it just grows exponentially. And that's the power of compounding. So the title of this slide is Power of Compounding. Alright, let's move on to present value again. Now, the R, rate of interest, which was 7% as we saw, is called the discount rate. And remember, now, instead of growing to find out the present value, we're bringing down the amount to the present value. So the discount factor is 1 over 1 plus R to the power T for the Tth, cash flow. Now, let's do an example. Tommy is 8 years old. He needs $100,000 for college at the age of 18 years. The rate of interest is 7%. How much money should he invest in order to end up with $100,000 for college? And so $100,000 is clearly the future value. 7% is the rate. And number of time periods is 10. How much money should be required today? So we use the same formula, CF1 divided by 1 plus rate to the 1 through CFN 1 plus rate to the n being 10. My present value is 100,000 divided by 1 plus 7 by 100 to the power 10. And notice I don't want any cash flows in the middle. I just want one cash flow in the end. So that's the cash flow I need, $100,000. 1 plus 0.07 to the power 10. And that means I need to have 100 times. Now 1 over 1.07 to the power 10, the value of that is 0.50835. And that times the initial starting value, 100,000, gives me $50,835. Which means if I start with $50,835 at 7%, I will end up with $100,000 after 10 years. Now, in order to play with discount rates, it can be shown in Excel that if we use 0%, 5%, 10%, and 20% with a present value of $100 for different amounts and at different times 1 through 20 years, we come to a graph like this. Now here, let me see. At 0%, for example, you will have to have $100 every year to finish up with $100 at the end of the 20 years. Now, the present value of $100 to be needed after 1 year at 5% interest rate is slightly lower. At 10% interest rate is slightly further lower, and at 15% interest rate is even more low. So what it tells us is that the rate of 15% is so high that I can start with a very small amount to be ending up with $100 after 14 years. I have to start with a higher amount at 10% because the rate of investment is just 10%. So I have to start with a higher amount at the rate of 10% to end up with $100. And I have to start with an even higher amount at the rate of 5% to end up with $100 after 14 years. So that's the idea behind this graph. So we've seen in this presentation simple and compound interest. We've seen present value and future value, and we've seen the importance of discount rate. That's chapter 5, part 1. Thanks for listening.